little glitchy to start. So here we go. We want VF. So, is there a formula that will give us final velocity based on the information I have at hand? What is it, if there is such a thing? VF squared, what we're looking for, equals VI squared, one of the pieces of information that we were given, plus 2A, which we're given, and D, which we know, because we're also given that. So even though we also know the mass, it doesn't show up in here as something that we need to take into account, so we're fine. VF is what we're looking for, so let's fill in what we know. VF squared equals, now it's falling, everything's going down here. So this is where, when you have objects that are starting to rise and fall, it becomes important to actually determine which way you want positive to be. And as long as we're consistent with that, it ultimately doesn't matter. So which way do you want to call positive in a question like this? Sure. If we call down positive, then my downwards velocity is going to be positive. The acceleration is going to be, and the displacement is going to be, well, it's being displaced downwards. This object, this 150 meters, is telling us that this thing, from its initial position to its final position, is being displaced 750 meters downwards. So that's also going to be positive. So we're going to have 15 squared plus 2 times 9.8 times 750, and we need to square root that thing. So how fast is that thing going when it makes contact with our arch nemesis, or this person's arch nemesis? 122 meters per second. So the mass didn't show up anywhere. That's kind of cool. That means something that we already looked at last week. Does it matter how massive our object is? As long as it's big enough to make air resistance ignorable, or you're in a vacuum, in which case Buddy Guy and Buddy Guy are both dead. If we're in a vacuum, or if the thing's big enough so that air resistance doesn't become a problem, we've got a final velocity here. Sorry? It's supposed to be Russia.
Oh, what's France's flag?
As France and Russia are very similar, one's sideways, one's up and down, and I don't remember the order of the colors. No, it's not supposed to be. It's not France.
No, because that's a lot of France is sideways. France is like vertical.
Yeah.
Russia
And Russia's horizontal.
Yeah.
That's why I kind of put them on an angle, because I wasn't, totally committing. I didn't know the order. That's why. Didn't know the order. And then time is easy. Time we've done before. How long was it before the enemy was hit? T equals question mark. You want to use information that we've already been given. You don't want to use information that we calculated in the event that we had to round. So do we have a formula that will relate VIA, VF, and VIA, our displacement, and T? Cool. And if you run that through again, if we call down positive, then we're going to have 750 equals 15 times T plus 1/2 9.8 T squared. That's going to give us a quadratic. That's fun. 750 equals 15T plus 1/2 9.8 T squared, which you can solve, or we could do what I just told you not to do, and use this formula instead. VF equals VI plus AT, and then we're going to get a value. Was this answer, was 122 exact, or did we round that?
I can look at my work. I didn't write it down.
Didn't write it down, okay.
I put the rounded on my work.
Okay. If you use the exact value that you got here, plug that in here, then you can just use that 15, the 9.8, and you can find T that way. Either way, The time should be,
Is 122.1679.172.
hold on, 122
Well, that's at least what my calculator was.
point what?
1679172.
1679172.
12.
Okay. So then from that number, subtract 15 and divide by 9.8.
I did do that. Where did I do that? Or let me just grab
10.9, is that an option?
yeah, 10.9. That's right.
10.9 seconds, there it is. If you solved the quadratic formula, you'd get a positive value and a negative value. Time can never be negative, so you want, because that means you're going backwards. That doesn't make sense. So you'll take the positive value from this, and it should also have been 10.9 seconds. So does the mass matter at all?
No.
No. The mass is given to us because the next chapter I could say things like, what's the force on Buddy Guy here as the anvil comes to a stop? Because the problem for him is not that the anvil is falling. The problem is that the anvil now must come to a stop, and he's the thing stopping it. So that's a whole section on a unit called dynamics, which is what we're going to start on the Monday we get back from spring break. I'll show you that F equals ma. This is the crux of all the dynamic stuff that we're going to do. The force is equal to a mass times an acceleration. So the bigger the mass, the larger the force, as you accelerate something from 122 to 0. And we're going to assume that the distance he's stopping it over is that, which is going to be his height. So we could figure out what the force on him from the anvil must be. That's the purpose behind giving us the mass. Sorry?
No, because how will we figure out if it's going to cripple him or not? It will.
That becomes a biology question. Let's do it. Okay, so let's add to this. This is a spoiler of what's to come, but the rest of it is all just more dynamic, or more kinematics rather. Let's assume, hold on. Let's give you some actual real world values.
I like that.
We like actual real world values.
Wait, and then we're going to have a test this week?
On Friday, yeah. Okay, so 1.7 meters is the height of this person. Okay, so we're going to assume that over the 1.7 meters, the anvil comes to a stop. So my initial, this is the second part of the problem. This is part C. So my initial velocity at this point, as it makes contact with his skull, is what? That's the 122 we calculated here. Now, it's going to drive him into the ground, coming to a stop. So we're going to get a distance. I want to figure out what the oh, and what else do we know? There's one more piece of information we have here. We don't need the weight yet. V final in this case is actually going to be 0. Actually, I shouldn't have scribbled that. We know the distance is 1.7 meters. We know that the initial velocity is 122 meters per second. The final velocity is 0. What's the acceleration? Well, I can use the same formula we used up here. Vf squared equals Vi squared plus 2AD. Vf is going to be 0. That's going to be 122 squared plus 2 times A times 1.7. What's A? Yeah, it's going to be big. You're squaring 122 and you're dividing it by 3.4.
4377.
Hold on. 4?
377.65.
Meters per second squared. So the acceleration of the anvil coming to rest is 4,377.65 meters per second squared. That is a massive acceleration. And then the only thing that we're going to add at the beginning of the next chapter is to say, well, there's actually a relationship between the force required to give something a particular acceleration and the mass of the object. That relationship is just the force is equal to the mass times the acceleration. So the force that this poor sap is going to have to give the anvil is going to be 43,776.5, and the units you're going to figure out are called newtons. And this becomes another biology question. If anyone looks up my search history right now, they're going to have questions. The force required to crush a human skull is 2,300 newtons, just to put that into perspective for you.
Oh, really?
Yeah. So we are in the neighborhood of 20 times the force required to crush a skull with a 10-kilogram anvil, dropped from a hot air balloon 3/4 of a kilometer up into the sky onto, and that is the height of Vladimir Putin. Assuming that's who we're dropping the anvil onto.
Got him.
Okay, so he's dead 20 times over. It's a good time. Not for him. So that's where we're at. The dynamics, it's coming.
Epic.
3 weeks from today. Were there any other questions about any other homework that I gave you? Yes. Sorry? Number 3. 3 is... Oh, 3 is very similar to an example I gave you. 3 is basically exactly this example. Balls tossed vertically upwards at 50 meters per second, except in question 3, I say the ball is thrown straight upwards at 28 meters per second. So the only difference between the question 3 that you're asking and this question I did as an example is this value is going to change to 28. You're going to go through the exact same process here. You've got a downwards acceleration, an upwards velocity, so these two cannot have the same sign. You called up positive here, so that means my acceleration was negative, and I want to know, question 3a, to what maximum height will it reach? At the maximum height, you need to recognize that final velocity is 0, and you'll figure out the maximum height of that object is, what did you guys get for 3a? 40 meters? Okay. And then how long does it spend in the air? Again, because, well, assuming, what does it say? From being thrown upwards to being caught. You can make the assumption that the ball thrown upwards and the ball being caught are doing what? They're starting and ending at the same height. So if they're starting and ending at the same height, you can do this. You find the velocity, the time it takes to get to the top, and then double it when the object starts and stops at the same height. And you'll find that the time taken to do that is like what, 1.5 seconds?
5.71.
Oh, really? That many? Oh, yeah, because it's going up and then coming back down. Right, 5.7 seconds. That makes a lot more sense. But it's exactly this example here. Does that help at all? Okay. And then question 8. Someone else was asking me about question 8. 8's exactly the same as 4, except you're not throwing it onto someone. You just fell out of a helicopter. So are we questions, comments, concerns with any piece of those part of the homework? We're feeling okay?
That's because that's what we're doing, right?
Sorry?
I think I want to give
You bet I do.
no.
Would it help if I gave one example first? Let's do the last example that I didn't do on Friday. But yeah, you got to assume that a quiz is coming. It's been a little while. I'm not quizzing you on VT graphs because that was what the lab was for. But, you know, we did another lesson, and I gave you some homework, and now there's no questions, so I want to see how good you are. So we're going to do a quiz. But the quiz is going to come after I do this example. So, how is this question different than everything else we've done?
Oh, because we have a height.
Yes, Eric. I see that hand. So it starts from a building. More importantly, it starts from a building and goes which way? It goes up first, and then it goes down. So this is where things get a little bit different, because we haven't had this before. We had thrown downwards from a height, but we haven't had thrown upwards from a height and then being allowed to hit the ground. The first example I gave you was thrown and caught, same height. Second one I gave you was thrown down. What happens if we actually throw the thing up? So that the path of our ball goes to the, it is a ball, is thrown up, and then allowed to impact the ground. So there are two ways to tackle this problem. Okay? And the trade-off is always going to be, in everything you do in physics, I haven't explicitly stated this yet, but I'm going to say it now. There's always a trade-off in physics. If you want to make conceptually the physics easier to deal with, the math will get harder. If you want easy math, you will get more. The conceptual physics doesn't necessarily get harder, but there is more of it. You will do more work for easy math. You will do less work with more difficult math. And it doesn't actually matter which path you choose to take. So we've got easy physics, hard math, or we've got easy math, more work. Well, I guess the easy physics is also less work here too.
Like the way that we most the math is difficult, most difficult. Like for example, you know the velocity is 0, and no, the acceleration is 5 meters per second. No.
So let's write down everything we know, because that's what Luis is trying to do now.
Yeah.
So let's do that. What do we know? We're not going to make a decision yet on which way we want to take this thing yet. Tell me what you know.
Distance is 10 meters. The velocity.
Sorry, what's 10 meters?
The distance.
What distance?
Like
Be specific.
the height of the building.
Okay, the height of the building is 10 meters. Cool. Okay, we know that. What else do we know?
Velocity is 5 meters per second.
What velocity?
Yeah. No. No. The I and the F is 0.
Hold on. We don't know that. In fact, we know it's not 0. Because this thing's going to impact the ground. It can't impact the ground with 0 velocity. Because that would have mean it has to have been starting on the ground with 0 velocity. And when you called VI equals 5 meters per second, you made an implicit decision. The decision you made was which direction is positive. Up. You called VI 5, which means this direction here is positive. So there's one more piece of information that we know for sure. No, we know it, well, more specifically than that. Connor.
The acceleration.
The acceleration is what?
Negative 9.81 on it.
Negative 9.81 meters per second squared. These are the only things we know for sure. Okay. And now, how you move on is going to determine what information you're allowed to use. Do we want the easy physics, hard math, or do we want the easy math, more work? Hands up for easy physics, hard math. Okay, let's do it. So, let's do it here. Number one. No, let's not do it over here. We'll do it over here. This will be number 2. This will be number 1. We'll do it over here because I need less space for it. So, easy physics, harder math means we're going to totally ignore everything that happens in the middle. All we care about is the state of the ball at the beginning and the state of the ball at the end. We're going to ignore everything that happens in between. So at the beginning, we've already got our information. We've got VI equals positive 5, and our acceleration equals negative 8.1. The only piece of information that we're going to add to this is what? We don't know what VF is. We don't know how long this thing takes. In fact, that's what we're looking for. We want what T is. What's the only other piece of information that we know for sure? And in fact, it's already kind of written there, but it hasn't been explicitly connected to the right concept. Sorry? No, we have that already. Connor. No, we already have that. It's negative the whole time. Manuel. Oh. Say it.
Is it the D is 10 plus something that we don't know yet?
I don't care about anything that happens in between. All I care about is the ball at the beginning and the ball at the end. D is, no, Zaid, keep going.
10?
No, it's not 10. Where is the ball relative to where it started? The ball ends 10 meters below where it started. I don't care about what happens in between. What concept are we talking about there? Displacement. Our displacement is negative 10 meters. And it's negative because you called, Luis, up positive, and the ball ends below where it started. So it has to have gone down. So the displacement's negative. We cool with that? You understanding there? Okay, so now we're going to relate, we have to figure out a way to relate D, VI, A, and T, because that's what we're looking for. D equals VIT plus 1/2 AT squared. Let's fill that thing in. D is negative 10. VI is positive 5. T is what we're looking for. Plus 1/2 negative 9.8 T squared. That, ladies and gentlemen, is going to turn into what? Kind of mathematical. That's going to be a quadratic. So I'm going to move this thing around. Actually, I'll do it step by step. Negative 10 equals 5t minus 4.9 t squared. I just took my half and I multiplied it by the negative 9.8. And now I'm going to move everything over to the left-hand side. I'm going to have 4.9 t squared minus 5t minus 10 equals 0. And now we got to solve that thing. This is not one of those ones where it's going to be a nice easy solve. Well, I can just divide by 4.9 and I'll get a nice little factor out, and then I find two numbers that multiply to the end, multiply to the end and add to the middle. The only way to solve this beast is to brute force quadratic equation this thing. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Completing the square won't help you. Completing the square only gets you the vertex up at the top. It doesn't tell you what t is. If I'm remembering it right, unless I'm not understanding how you're going to use it. Because you don't want, completing the square gives you this vertex. You don't want the vertex, you want the roots. You want this value right here. So if you use the quadratic formula, you're going to get two values. You're going to get a positive and negative value. So let's plug this thing in here. I have negative, b is negative 5. Let's go plus the square root of negative 5 squared, b squared minus 4 times a times c. But then I got to make sure that I'm actually dividing the entire thing. So I'm going to go back to the beginning. I'm going to add another set of brackets. So I've got my negative b plus the square root of b squared minus 4ac, close that bracket on the outside, over 2a so there's that. That value is 2.027, which I'll round to 2.03 seconds. So again, it's one and done. It's way less work. But if you're not comfortable solving the quadratic formula, this is going to freak you out, going from this step here to this step here. So the math is slightly more difficult. There is another option. Hands up if we're cool with this. You're like, yeah, I'm happy with what happened there. Okay, I don't particularly care which path you choose to take, but you need to be comfortable with the method that you choose to use. If you like the quadratic formula, use it. Here it is. If you don't like the sorry?
How much is like between the two x's? Because
sorry?
in quadratic formula, I get two x's, so.
Yes, you do. If I, oh shoot, how do I go back on this thing? I don't want to type it in again. No!
I had one of those tries today. That's the right thing, not the side.
Sorry?
Move it so I can see.
Oh, maybe it's this. No, it's not. It's this one. No. It's...
Yeah, I have no idea.
Graphic calculators can do it. Apparently this one can't. Okay, so if you found a negative answer, so Luis, the reason I picked the plus answer is because that's the one that I knew was going to give me my positive value. If you're using, wait, was it Luis that asked the question? It was Luis that asked the question. If I had chosen the negative value, like instead of going plus the square root, if I had chosen the minus the square root, I would have gotten a negative value. And that negative value, because this shape, the shape of any object being thrown into the air, doesn't matter how narrow it is, like even if the ball lands right beside the building, this is still going to be a teeny tiny parabola. So what the negative value gets you is this time here. If I were to follow the same path of the ball but go backwards in time, or what time would it have been at ground level going backwards in time? That's what the negative value would give me, and it doesn't make, conceptually, it doesn't work, doesn't make sense. So we ignore the negative value. So the other option is to make the math a lot easier, but the question a lot more difficult. To make the math easier, but not more difficult, but more work. There is one, if I start caring about what happens in the middle, there's one location where we know, actually there's two locations, where we know some pretty important information. What other two spots on the path of the ball could we talk about specific values for things? At the top of the arc, what can you tell me about the ball? At this point right here, VF is going to equal 0. This is the location that is actually really useful to us. There's another location that is not useful to us, and in fact, you never ever want to touch it. And that would be this location right here. How fast is the ball moving right there?
I think it's the same as the start.
The same as the start, except downwards.
-5.
It's going to be at this point, it's going to be -5. We could use that, but you don't want to. Anywhere where you have information where something you know is equal to 0 is where you want to hang out. So what we're going to do is we're going to split the problem up. If you don't want difficult math, we're going to split this problem up into 2 steps. Step 1 and step 2. We're going to find out how long it takes the ball to go from here to here. And then we're going to find out how long it takes the ball to go from here to the bottom. We break it up into two separate parts. And then what we're going to do is we're going to find these 2 times, and we're going to add them together. So, for the first half of the problem, we know that VI equals 5, we know VF equals 0, and we know that the acceleration is negative 9.8. We want to find time. So there's a relatively easy quadratic equation that we can use. VF equals VI plus AT. VF is 0, VI is positive 5, minus 9.8 t. I subtract my 5 over, so I'm going to get negative 5 over negative 9.8 is equal to t, and we're going to have a value for t of, I have it written down here, 0.51 seconds. That time, one second. Come on.
Got this lead off.
I think it's gone. I hate it. You lose a sneeze. This time right here is the time it took the ball to go from where it was first thrown to the top of the arc. Half a second. Now, we're going to start up with the second half of the problem. With the second half of the problem, what's VI? VI becomes 0 for the second half of the problem, because the second half is just, I'm here, now I'm falling to the ground. If VI is 0, I also know that my acceleration is negative 9.8 meters per second squared. What else do I know? Do I know anything else? I don't know anything else. So we're missing some information. What information do we need to know to be able to figure out how long it takes the ball to go from here to here? Either VF or the displacement. How far the ball travels from here to here. Do I have any hope of finding VF? No. So I have to be able to figure out what this dropped distance is. How do I do that? Naya, do you have a thought?
With the things that you got in the first part, you do the distance there.
Oh, Luis, you're suggesting that now I've found the time, so I'm also going to find this distance. Yes? Is that what I'm hearing you say? You betcha. Because once I find this distance, what am I going to do to it?
You just add it to the whole distance.
I add it to the 10, and that's going to give me the entire drop. So now we got to go back, we got to find out what this displacement is. Well, that's relatively easy to do. Now I just want to relate VI, VF, A, and D. So that's just going to be VF squared equals VI squared plus 2AD. VF is 0. That's going to equal 5 squared plus 2 times negative 9.8 times D. That's going to be 25. I'm going to subtract it over. So I'm going to get negative 25 divided by negative 19.6 equals D. And I'm going to get a value for that of, where are you? 1.28 meters. Sorry, Connor?
Well, that's pretty good. In your head like that.
I would hope you all could. I hope.
No, I knew the formula in my head. I didn't think like the 9.8 doubled.
That's going to become a number that you're going to become very familiar with.
Yeah.
You're going to get real comfortable multiplying and dividing 9.8 by 2. So that's going to be 1.28, which means that the entire distance for part 2 of the problem is going to be what?
11.88.
Almost. Which way is the ball going? It's going to be negative
Oh, so it's minus.
11.28 because the thing is falling down. And you said, Luis, at the beginning of the problem that up was positive. So that's the only difference. Because we took this value here, we added it to this, and now the ball's fallen down. So I've got VI, I've got A, I've got D, and I want to find T. It looks like it's going to be gross, because the formula that does this is D equals VIT plus 1/2 AT squared. But what's the beauty of what we've done? VI is 0. So this term is gone. So we're going to get negative 11.28 is going to equal negative 4.9 T squared. 11.28, negative 11.28 divided by negative 4.9, and then square root that thing is going to give us a time of 1.52 seconds. And then to find the total time, I'm just going to add these two together, the 0.51 and the 1.52. And you're going to find that that value is going to be 2.03 seconds. Which, it better be the same result. Because I can't do the same problem 2 different ways and get 2 different times. That would be weird. But we can see here why sometimes the more complex mathematical operators are really useful, yeah? Because if you don't do it this way, you have to do it this way. There is no other way to solve this problem. Cool? Comments, questions, concerns? Is there any, at this point you know there's a quiz coming. Are there any questions anyone wants to ask me before we do this quiz? About anything? Okay, here we go.
We didn't do an attendance question.
You're right, I didn't.
Let's do that real quick.
Nope.
Wait, did you do
Okay.
attendance?
Sorry?
Did you do attendance?
I have not yet done attendance, no.
You should do it.
I will.
Right?
While you're doing the quiz.
Chill.
It's coming, don't worry about it.
You got questions, man.
Okay.
Give me questions.
Because you guys are block, oh crap, you're block C. Dang. Which means we don't have class tomorrow. We have class on. You know what? I am not going to give you the quiz.
Hey!
No quiz. Here we go.
You're the best.
Flip, find me this page here.
I was kind of ready to add on a formula. Oh, that was mean.
Here we go. No quiz.
You playing with my feelings too much, Mister.
Oh, just wait. Yeah. What I'm going to do to my math 9s later today is nothing compared to what I just did to you. Emotional whiplash. They're going to find out that they have a test first block Monday after spring break today, and they're not going to love that at all. Gerkiret. Yes, I will give you the quiz just for homework. Yes. Oh, I'm so glad you were here. Everything you need, you're still able to do it, yeah?
Yeah.
Okay, cool.
Yeah.
Everything you need is on the table at the back. I printed off a couple pieces of paper that just say Abby's Got Talent Audition sign up. Just tape those to a desk or a table down in the rotunda. I've got the sign up sheets with, I think it's 4 slots for each day, and I gave you some tape and a pen. So it's all right there on the back. Thank you so much.
Do you have an extra note sheet? I wasn't here on Friday.
Yes, I do. It's on top of the pile on the top of the filing cabinet. It should, yes, it should start with acceleration due to gravity. Oh, that doesn't, that's the wrong spot. I put it in the wrong spot. That's okay. But that's it. Yeah, I put it on top of my math stack. I shouldn't have done that. Okay, so here we go. This is the last thing that we're going to do out of kinematics. So if I can get it done in the next half hour, this is going to be the last lesson I give you. I'll give you some homework. Wednesday, you will come back, because we don't have class tomorrow because of the short day. You only have A block and then B block. Wednesday morning, I will go over the homework that I've given you here. And I will give you guys the chapter review. You will spend the rest of Wednesday and our block on Thursday doing chapter review of all this stuff that we've done this first unit. And then Friday before the break, you guys are going to write me a physics test. You guys have class, it goes tutorial, then A, B, C. So if you feel like you're not going to be able to get it done in the hour and 5 minutes, that is the short block, you're welcome to start at the beginning of a lunch on Friday. That'll give you an extra 40 minutes. And you're welcome to sit in here and eat while you work. So yeah, like I said, it'll give you extra 40 minutes to work on this test. But it has to be written on Friday. So it's not like you can start it and then, not finish it that day. Yeah.
Will there be a bachelor review?
I did just, yes. You turn things off sometimes? That's not super useful. Yes, I did just say that we were to spend Wednesday and Thursday reviewing. And so I will provide for you.
Thank you.
Yeah, don't turn off. Do your best to not tune me out.
I really don't.
Especially when I'm talking about your test. That's on Friday.
Is the test like questions, or I need to write a full test about the chapter?
Yes, it's questions.
Okay.
Yeah. Multiple choice section, written sections can be great. Okay, here we go. So projectiles. This is where things end here. A projectile. The definition of a projectile is anything flying through the air where gravity is the only, and this at this point I'll just call it a thing because we haven't really talked about forces. It's the only thing acting on the object. So anywhere where you've got something else acting, this is not a projectile, as far as physics defines it. So an airplane, is an airplane a projectile? No, because what's acting on the airplane? The engine, okay? Obviously gravity is as well. If I cut the engine on an airplane, it's going to turn the sucker into a glider. Can you ignore air resistance on a glider? No, that's the only reason a glider is doing its own thing. So even then, a glider, also not considered a projectile, because you've got the air and you've got gravity acting together on this thing to keep it up in the air as it floats around. Like a rocket launch. The rocket considered a projectile? What if I cut the engine on a rocket? Rocket's got no wings. If I cut the engine on a rocket, does that thing become a projectile?
Yes.
Yeah, you bet it does. That's the, yeah, I think those examples are sufficient enough. That's the fundamental difference between a projectile and literally anything else we're talking about here. Projectile focuses specifically on things where gravity is the only thing acting. So we've got a couple styles of problems for projectiles. We got simple ones. One, the simplest form of a projectile problem is what? No, that's actually fairly complicated. The simplest type of projectile question, anything flying through the air where gravity is the only thing acting on the object, is if I take an object and do what with it? Drop it. This is the simplest form of projectile. I have dropped an object, an anvil, perhaps, out of a hot air balloon onto a dictator. Projectile. I could ramp this up a little bit here and say, okay, well, instead of just dropping it, I'm actively throwing it. Those are speed lines. Implication there being, here VI is 0. Here, I've given it some VI downwards. The next kind of problem that we could look at for a projectile, if I wanted to make things a little bit more challenging, is to do what? We're never going to look at air resistance. Even before then. Easy is drop. Next, throw down. Slightly more complicated, the upward throw. Give it some speed lines. Slightly more complicated still, the upward throw from a height. This is where we're going to go now. What if I take my object, instead of throwing it straight up off a building, I throw it perfectly sideways? And then, sorry, I got one more for you, Luis. If I really wanted to make it fun, I could take my object and do what with it? Yeah, I could launch it up at an angle. This is the nastiest kind of projectile question I could give you. In between, there's two in between here. I could do one like this, off level ground, but at an angle off a building. This is the nastiest kind of stuff I could give you, and this isn't going to show up until grade 12. No, I just finished saying it's going to show up in grade 12. So this is what we're going to do now. This blue one here is what we're going to talk about now. So if I were to throw an object sideways and drop an identical object at the same time, which one is going to hit the ground first? So let's draw this out. I've got an object that I'm going to drop, and I've got an identical object that I'm going to throw sideways. Which one of those two objects is going to hit the ground first? Connor. Hands up if you agree with Connor. The object that's going straight down is going to hit the ground first. Okay, hands up if you disagree with Connor. Nobody disagrees with Connor because a whole bunch of you didn't vote. What are your options? Because we only really talked about the one option and a bunch of people put their hands up. The one option is this one hits the ground first. Another option is this one hits the ground first. And then the last option is these things actually hit the ground at the same time. So let's see, maybe we can actually demonstrate this. Oh, come back. So they're not exactly the same, but they're effectively the same, right? So like mass is definitely not going to be, we've already established that mass is irrelevant here. But these are big, yeah, roughly the same way. Basically the same size. The Hubble is a little bit smaller, but not much. So the really easy way for me to demonstrate how this is going to work is actually, I'm going to back the cluster, got a little bit more space. I'm going to take this desk, and here's what I'm going to try and do. Because it's really hard to throw sideways perfectly and drop an object, what I'm going to do to give this object a little bit of horizontal, shall we say, I'm going to roll this thing. And it's going to roll to the edge, and then it's going to fall. Okay? So are we cool with this being the same thing as what I'm suggesting up there? A little bit of sideways motion, and it's going to fall. I'm going to try and time it so that as this object rolls off the edge of the table, I'm going to drop the baseball. This is difficult to do, but I'm going to try. Okay? And we're going to see which one of these things hits the ground first. So, do this. The base is level. Which one hits the ground first? Drop it a second. Does anyone think that I scammed them and want me to do it again?
You can push like harder. I think the
Possibly. We're falling away. Okay. Sorry, Karen.
I think that if you push harder, just fall.
No, harder. Okay. Here we go. Do it again. You want me to push it harder?
Yeah.
This is even harder. Okay, here we go. Luis wants it faster. Okay, let's try again. The hard part is timing the drop. Is it making a difference, Luis? Sorry? No. So does it actually matter how fast the horizontal object's moving? No. If we had more time, I would show you, and I'll link it to our Google Classroom. Mythbusters actually did an example of this, where they took exceedingly fast objects, took a handgun and a bullet, and they shot the gun and dropped the bullet at the same time. They didn't arc it with a perfectly level handgun shot. They had a whole apparatus for this. And they fired the bullet, and as the trigger was pulled, another bullet was dropped. You'll see in the video that they actually managed to get them to hit the ground, because bullets don't fly forever. Bullets have no wings. A bullet is a fantastic example of a projectile. The only thing acting on a bullet is gravity. They managed to get it so that they hit the ground within 1/1000th of a second. Verifying, I'll link it to the Google Classroom. I don't have time to show it to you in class today. That it doesn't actually matter how much horizontal speed an object is given. A falling object and a horizontally moving object, if dropped from the same, or if starting at the same height, are going to hit the ground at the exact same time. Why is that? Do you think? Connor.
Because all it's sitting on is air, so even if it's moving a straight distance, gravity's still acting on it. There's nothing from keeping it from going down, so it's really just falling at the same rate. The only thing that's changed is one's moving forward while falling, which isn't changing it.
You're right. You're right. No, you're absolutely right. So, how do I explain? Connor, how do I write concisely what you just said? Because you're exactly right. The idea here that Connor is trying to, I think, articulate is that gravity acts the same on both objects regardless of horizontal velocity. This is only true for projectiles, which is why I specified what projectiles were right at the beginning. Projectiles are anything where gravity is the only thing acting. So if I gave this ball wings, now all of a sudden I'm providing it with some lift, it wouldn't work. what I need here are two objects that don't have, there are no wings, there's no lift. They are true projectiles. There is an interesting little result that pops out of here. And the interesting result is that horizontal and vertical velocities are independent of each other, which is kind of cool. For this object here, what do we know is true? If I'm going to turn this into a kinematic problem now, what can you tell me about this object right here? The acceleration for this object is negative 9.81 meters per second squared. Initial velocity is 0. And I don't know what the height is, but let's just call this d. Don't know what the final velocity is. What can you tell me about this object here? But can you tell me anything about the VI? VI down equals 0. VI horizontal, I'll just call that VIY. Sorry, VIX. VIX. What else can you tell me about this object here? I think Zaid's opened up an interesting part of the discussion. Because horizontal and vertical velocities are independent of each other, I can split the velocities of this object up into a horizontal piece and a vertical piece. What else? Now I can specify that my acceleration down, Luis, you just said it was negative 9.81 meters per second squared. What else can you, well, can we talk about the acceleration horizontally? Assuming we ignore air resistance, what's the acceleration horizontally? Think about the ball rolling off the table. Was there any acceleration to the ball rolling off the table? There was no acceleration on the ball as it rolled off the table. And if there was no acceleration on the ball as it rolled off the table, does it make sense that there would be a horizontal acceleration as it flew through the air? No. So my acceleration in the x direction is also going to be 0. I had an initial velocity downwards of 0, and now I've got a horizontal acceleration of 0. What else can you tell me about this object? Let's keep breaking things up. Sorry? So this one's going to have a V final, and this one's going to have a V final down. Luis is telling me that these two are going to be equal. That is true. If this thing has no horizontal acceleration, V final is going to be the same as VI in the x. VFX is going to equal VIX. That's cool. And there's one more piece of information that we can split up like this. Yes, there it is. The distance?
the same.
Which distance?
The displacement
Displacement which way?
down.
So I'm going to have a displacement down.
Oh, now I get it. Like the displacement horizontal is going to be different. The only thing that
Is going to be this here. But this thing is also going to have, I'll call it dx. We don't know what that is, but we have a name for it. What do we call the horizontal distance that an object travels while thrown or shot? Starts with an R. Almost. RA. It's the range, which is a word that you should be familiar with.
FPS games or
Those are you're abusing vocabulary. That's not true. And when you think about range and domain like that, that's a horrible way to think about them, because that's where you get confused about things like this. Domain is not horizontal. Domain are all acceptable input values, and range is all acceptable output values. How you arrange the graph, that is the definition of domain and range in math. How you arrange the graph is going to determine whether those are horizontal or vertical. Careful. Are there questions about any part of this so far? This is where we're going to stop. I was going to go here in a sec. Your homework for today is this. The quiz that I was going to give you.
Good morning, Abby. Here are your morning announcements. We will start off
Oh, yeah, let's hand these things over. You're going to hand this thing in to me on Wednesday when we have class. Oh. Okay, we'll finish the projectile stuff off on Wednesday. What the time that remains on Wednesday, Thursday, we'll review. Your test of the stuff's going to be on Friday. Have a great day, guys. When the bell goes, you may also go see Wednesday.